Hello and welcome back. In our last video, we introduced R and RStudio and some of our motivations for wanting to learn this coding environment for data analysis. In this video, we're going to just jump right in and start using R through that RStudio interface that we discussed. Now remember, in the last video we mentioned you're not going to use the R app that comes when you download R first, or the R GUI on Windows, or indeed R at the command line in the Linux environment, but we're going to use this thing called RStudio, which is a separate download and a separate interface called an IDE for running and interfacing with R. So please make sure you open that now. Make sure you open RStudio from your start menu in Windows or from your applications folder on Mac. And once you've got that open, you should have a window much like the one behind me here. We're going to focus in on the main console window of RStudio. That's the R brain. How do you know that, which panel is the console window? Well, it's this one right here, and it says console right on the top. So please click on that. We'll pause here the video to make sure you've got this open, and you can see if you can type in this console window. Now I'm going to do one thing here. I'm going to click this little broom icon to clean up the console from any droppings I might have from the launch screen when R starts itself, or anything that I might have typed in previously. So I'm just going to click this little broom to give myself a clean console that's not going to distract us as we go through the next few examples together. So focusing in on this R console window, I'm going to start by typing some simple math into our console window to see how R responds, to see how R works, what kind of feedback it gives it back. So I'm going to start here. I'm going to type some math, 2 plus 2 in this case, and then I push return and it's going to spit back an answer at me. This is the result of the command. I'm going to do 3 squared. You see the little hat symbol here that on my keyboard, let's see where that is. That's, if I do shift 6, that will give me that one. I'm going to do some math with brackets here. So 2 times 1 plus 1, which it does the 1 plus 1 first. So it's 2 times 2 will be 4. Okay, so this is, works the way we would expect math to work. If I didn't use the brackets or the parentheses here, it would go and do something maybe that I wouldn't intend, like 2 times 1 is 2 plus 1 is 3. Maybe not what we wanted in this case. So math works the way we are hopefully expecting math to work, this order of precedence that we normally deal with when we do multiplications and additions, these sorts of things. Now moving on to do something a little bit more useful in R, and again, the features of R, we can think of those as the functions that we use in R to do stuff, whether that's some mathematics thing like run a blast search or do a differential expression analysis, or here let's just go and do the exponent. Let's calculate the exponent of a number, like the exponent of 1 here. So we're going to type our first function call, and we copy its name, and then we give the input to it inside parentheses. So 1, and then push return, and it gives me the answer, in this case 2.7182 in this case. Now I can take the log of that answer by passing the input as a function call itself, or I could do it the way you would expect, just give the number as I'm doing here and call log, and it'll spit back 1. So this log function looks like it's returning natural logs. It's not log to the base 10, because if I type log 10, I would expect that to be the answer 1 if this was log to the base 10, but it's natural logarithms. I can argue with this function to make it do what I want if I wanted log to the base 10, as in this example here. So as we get more comfortable with using functions, we'll add extra arguments into them. These arguments are separated by a comma. They're given inside the parenthesis, as we're doing here with the log call, and they'll change the way the function works and potentially change its output. How do we know what arguments are available or how we can argue with these functions? Well, we look at the help page. How do we get the help page? Well, we put a question mark in front of whatever it is we want help on. So here I'm going to look for help on this function called log. So I'm going to write question mark log, I push return, and it opens up this help panel here with the inbuilt R documentation page for this function. I'm going to click on this little icon here, the pop-up menu icon just to make it a little bit more visual, a little larger in my window, and I get a larger view of this same help page here. Right at the top of all of these help pages, there'll be the name of the function. In this case, it's log, that's the one I asked for. And then we have a description. And this description can be a little nerdy, as we see here. Log computes the logarithms. Okay, we get that. By default, it's natural logarithms. That's kind of what we saw from the calculation, what we expected. Now note here, in this case, and this is the case in a number of different functions, when we have similar functions available, like log 10 or the exponent function, which is obviously related to the log function here, they're often documented together. So we have multiple functions described here in this one help page, as we see here. The next section is probably the most useful one so far that we've seen. This is the usage section. This tells you what are the available arguments, what are the named inputs that I can give to this function that would change the way it works potentially, right? This will tell us what the default values are. For example, in the log function here, it takes something called x. We'll see below in the argument section that that's a number usually. And then base is the positive number that you want to calculate the logs with respect to. And by default, that's the exponent of 1, so natural logarithms. So the usage together with that argument section here go kind of hand in hand to tell us how to drive these things. And then if we scroll down, and I'm not going to do it here for the sake of brevity, but you would see more description, more details, related functions that you could click on to link to their help pages. And then one particularly important section is the example code section. That will show you real working code examples of using this function kind of in anger. Now we'll not dwell on them here because we haven't seen too many functions yet, but as we get a little bit more advanced and go through learning more R code, we'll often turn to this example section for inspiration to see how these things work. So let's move on. Because beyond those kind of help pages, which for brand newcomers like ourselves learning R, quite frankly, they're not the clearest for newcomers. They're written by nerds, and nerds are in this mindset where they're writing for other people like themselves, so other nerds. So they're maybe not writing in the clearest, most beginner-friendly way on every instance, and that's certainly the case for that log help page that we just saw. So don't be shy about it. Everyone does it. Just go online and search with Google. So here I'm searching for R log function, and there'll be lots and lots of accessible online resources to help you learn or help you use and show you examples of using these kinds of functions. So just look it up. Don't feel bad about it because everybody does it. So let's move on. Let's create our first R object or variable here. We're going to call it x, and I'm going to give it the values 1 to 50 as shown here, and I'm going to then print out the values of x. So I'm going to type here x 1 colon 50, so then I print out x, and I see that it's got these values 1, 2, 3, 4, etc. consecutively all the way 49, 50. Now notice the little square parentheses or brackets, the numbers at the start of each line here when I printed out x. 1, 17, 33, 49. Now what are these? Well, you might have noticed square brackets 1 in the previous examples that we did because we were returning an object that only had one thing in it, so we only saw 1 printed out here. Now we're returning x and it's got 50 things in it, so it's telling us which element, the number of the little bucket, the element of the vector that's going to be printed out next on the new line. So there's 16 numbers on that first line, and then the next digit will be the 17th entry, and then there's another 16 on that, so the next entry is going to be the 33rd, then the 49th, etc. Right? So we'll come back to that. We'll describe what a vector is, what the elements of a vector mean. We'll describe all that terminology in a couple of moments. But for now, just think of it as giving us a little handle upon what's been printed out within our objects. So let's take that vector x and use it as input to another function called plot, which you guessed it, makes figures, makes plots. And I'm also going to provide a second argument into this function. So I'm going to plot x versus the cosine of x. So cosine or sine, and I'll use sine of x here maybe. Just like trigonometry, if you remember the sine, the cosine, etc. from your trigonometry in school. And what that'll do when I plot it here is it'll make this little scatter plot, and it's a bit dull. Okay, we've got the numbers 1 to 50 along that bottom axis, and then we've got the sine of x along that y axis here. Now this is not actually what I want. Just like the log, the natural log that was returned, and I wanted log to the base 10, this plot isn't what I want. So I'm going to argue with it to change its behavior. And I want a kind of line plot, to show that kind of curvy, sinusoidal kind of line. So I'm going to look it up in the help page, and I'm going to add an argument to it. So in this case, I'm going to recall my command. I'm going to push the up button, and then I'm going to edit it. Type equals L for line. I push return, and I get a line plot in this case. Now, this is not that exciting yet. I'm going to maybe I don't like the colors. I'm going to change and argue with it again. I'm going to re-execute this by pushing the up arrow to recall my last command here. And then I'm going to delete back and add another argument. So comma, the next argument, call equals blue inside quotes, push return, and I get a blue plot in this case. The line is colored blue. Now maybe I want to do a thicker line, so maybe I'll make the line 3 times the thickness here. So I'm going to recall it again. I'm going to do line width equals 3, and we'll see a thicker blue line appears in my next plot. So what I'm doing here is I'm iterating on it. I'm arguing with it at each step. I'm not typing everything out fresh, but using the up arrow key on my keyboard to go through the history of commands that I've entered. You'll notice that if you push the up arrow key many times, it'll bring up the previous commands in order that you've typed since the last one, and then edit it, push return, and see the effect in the graphics window here. Now, I'm nerdy, so I kind of knew what those arguments were to change the way this plot function worked, to change its width, to change it to a line, to change its color. But where would you go to find them if you didn't know them beforehand? Well, the answer, of course, is the help function, question mark, the name of the thing you want help on, in this case, the plot function. So I'm going to do question mark plot, push return, and that's going to bring up this help page for the plot function. And this function or function's help page here gives me some details of what it does, generic XY plotting here. It also gives me a link so I can find out more about different graphical parameters. I see that both in the description here, but also down in the arguments section. I'm highlighting it in the red here. So I'm going to click on that, and it's going to bring me to another help page. And this is actually probably the most overwhelming help page in all of base R. That's R that comes out of the box when you install it first. This is the power function, and there are hundreds of arguments that we can add to these plots to change every single little damn thing about the kind of plots that are made here. So see how small that little scroll bar is here. If I start scrolling down this thing, it's huge. There are hundreds of things here, all in alphabetical, like the background color, the CX, the character expansion, the type of color of the ticks, the size of them, the font family, the background font, and all sorts of things, and whether the axis label should be perpendicular, and things like these things that I've never actually used before, like the join style of lines when lines meet. Like if you're a carpenter, you might want to round or bevel or miter the edges of wood. You can do that here in R with the lines and the figure margins and all sorts of things that allow you to change pretty much all the aspects of the output of these functions. You have ultimate control over every pixel nearly that goes in these things. Now, I don't expect you to remember all these kind of arguments for these functions, but I do expect you to know how to get help on them and look them up if you need to. And remember, you can always use Google and search, how do I make my line thickness in plot? And Google will tell you or bring you to a page that will give you hints to that effect. Now, I played with this a bit and used some arguments here and made my plot look very different just for demonstration purposes. And It kind of matches my color scheme that I like, that I use in a lot of my slides here. But even I admit that, this is about as much style as Ron Burgundy has here, and I kind of regret taking this too far here. But the point is, you have control over everything in these plots, and a lot of these functions, you'll have arguments to control the way they work. How do you find it? You look in the help pages to explore how these functions work. Now, these plots, like the ones we're making here, they make viewing your data easy, right? You type plot, the name of the thing you want to plot, and off it goes. You can, of course, spend more time and change the way it looks, like Ron Burgundy would do here, right? But you don't have to. You can always generate super impressive presentation plots like the one I made here with extra packages like ggplot that we'll learn a little bit later in this course. In this course, what we're doing here is we're plotting some different data sets that all have the same summary statistics. We'll talk about how we calculate these things in our next class, including the mean in X, the mean in Y, the standard deviation of these different data sets, the correlation values and things like that. So they're all the same for these different data sets. And if we were just relying on summary statistics, we would think, oh, this data is the same as it ever is. Let's just continue with our analysis. But if you just plot the damn thing, you see that the data looks very different. And you wouldn't know easily from just looking at some numbers, some summary statistics, that there was a dinosaur hiding in your data, ready to roar at you at a later point and make your life difficult whenever you start to do analysis where you didn't expect your data to be strange like this. So the key point here is we need to be able to visualize our data quickly to both spot interesting patterns but also see potential problems. And just calling the plot function will get us that. Quick plots that we can iterate on and explore our data. This is going to be the subject of our next week's topics, all about data visualization, plotting, and analysis. So I'll leave that topic for then, but I'm just going to say that we can create really beautiful, compelling, of course, animated figures as well as static ones like these ones here in R. But before we get there, before we start making these beautiful kinds of data visualizations and figures here, we need to know how to store our data, how it's encoded in R, so we can get the bits of our data out that we want to use for that analysis or that figure or that plot or that statistical procedure that we're going to do. Now, there are a number of major data structures in R that I'm listing here. You can just think of these for now as just containers for your data, the stuff we want to actually analyze. We're going to focus on just two in this video, that's vectors, and then we'll also talk about data frames. So vectors are the most basic data structure in R. We already created one when we created X there, that a 1 to 50 vector here. Here we're creating another one called myVec. We're just making up that name, and it's going to have 4 values in it, 4 numbers. So in this case, it's just a little container, a one-dimensional container with those values in each of those elements of the vector in order: 11, 1, 2.5, 4.5 here. So if you want to get some data out of that vector, you can use the square brackets syntax or nomenclature. If I want to get the value in that third little element or bucket in the vector, I would use the name of the vector, square parenthesis, square brackets, the element that I want, in this case the third one, and that will return my value. If I wanted the first element, I would use 1 here. These things are indexed starting from 1. That's important to note here. Now, there are lots and lots of functions that take vectors as inputs. For example, here's one. I'm calling the length function on that input vector, and it'll tell me how many elements are in the vector, or in other words, how long it is, right? How many little buckets there are in it. In this case, it's of length 4. There were 4 entries in this vector. I can do numeric things, numeric summaries, like the sum here, for example. This will sum up or add up the values within the vector. So 11 plus 1 plus 2.5 plus 4.5 equals 19. I could take the average here with the function mean. This will calculate the mean value of all those within the vector. Or SD here, that's not San Diego, that's standard deviation, right? Another summary statistic. So all these functions, and there are many others, they'll work on a vector as a whole and compute something from it, like a summary statistic in this case. Now, where R starts to get useful is when functions work on the individual elements of a vector all in one go, kind of for free for us. That is vectorized functions. That's the name that we give to these functions that will work on every element of the vector all in one go. So here we have some examples of this. We have the same little input vectors before, but this time these functions, I'm just listing a couple of examples here, they compute something for each element of the vector. So you see here in each case there are 4 answers corresponding to the 4 elements, whether it's the square root of each of those elements in the first one, or the natural logarithm as in the next example, or in the final example here I'm taking that natural logarithm and I'm passing those 4 answers for the natural log to the round function just to round them up to the nearest whole number. Now a question here for you to explore in your R console is, how would you do this calculation but round to 2 significant figures? Well, the answer is you're going to have to look at the help page of the round function and figure out how to argue with it to tell it to do that. So I'm going to leave that as an example for you to do. What argument would you put and what would it look like for 2 significant figures? How about 4 significant figures? I'm going to change the value to that argument. So an important point here, and one that I haven't mentioned yet but I need to, is that vector elements must all be of the same type. So the example that we were just working on in the last slide here were all numbers. They were all numeric values, like that x equals 1 to 50, or that little 4-element vector that we were just calculating those summary statistics from, or the square root or the log, those things. Those were all numeric vectors. Now here, this next vector, this example, these are character vectors. So they're all kind of word-like things, right? They're strings, character strings. Or in this last example down the bottom here, I have what's called a logical vector. These are all different data types, numeric, character, or logical in these cases. And so vectors have this limitation where all the data within a vector has to be of the same type. Okay, if they're not the same type, they'll be coerced. And R will do this for you rather silently. It'll try and save your ass and convert them to the most flexible data type. But this might not be what you want. You know, most times that's going to convert them to character strings. Like in this case, I have a number 1, and then I have a character G, and then I have a 4 here, but I've got the quotes around it, so it's actually a character 2. Then I have a number 0.05, and then a logical, one of these true-false Boolean values. What R is going to do whenever I enter this in and then tell me to print it out, it's actually going to return a character vector, and it'll look just like this: 1 with quotes, G with quotes, 4 with quotes, 0.05 with quotes, and true with quotes. These are all strings. So that means I can't do math with it anymore. I can't, for example, call the sum of it, because it doesn't make sense to sum up characters, right? What's the sum of a G and a true? That's not sensible. So it'll give you an error message. And the error message will look something like this. It'll say something about the type being invalid, because you're mixing types. This character type can't be put into a function that's expecting numeric values as input. So, okay, one last thing about vectors before we move on here is that we can add names to each element of a vector. And you can do this either at the time you create the vector, like here I'm creating this little vector of 4 things when each one has got a person's name on it, where these are, you know, fictional students in some test, and that's their score. And it'll give me a character vector like this, where the names come along with each element of the vector. Or I could do this after I've created the vector, as in this example here at the bottom, where I'm creating the vector first, and it's got 4 numbers in it. And then I use this names argument here to add the names, a character vector of names that's the same length as the original vector of grades here. That'll give me the same thing. So I can either do it at the time of creation or do it later with this names function, which can either set or query or change the names attribute of a vector. Now, why would this be useful? Well, because it means I no longer have to remember where I put a particular element of data in the vector, right? So in this case, for example, I could say, well, what did Barry get in this test? I could do that. I wouldn't have to remember that Barry was the second student enrolled in this class or the second person that submitted their homework or whatever it is. I don't have to remember that it's the second element of the vector. I just ask for it by name. Tell me the grades that Barry got, and it's in this case 99. I can also because these names come along for the ride when I use various other functions, like here when I'm looking for who got the maximum, the top score, which dot max, it'll tell me Chris got the maximum score. That was the 4th position in the original vector. Damn it. Obviously there's a fault with this test. Why did Barry not get the top scores? That's besides the point. We could also do something like sort the students here. For example, if we wanted to rank or sort the students by their score, those names come along to show me that maybe Chandra we want to follow up with and see how they're doing and what the misconceptions were in this particular test. And Chris, we need to check why Barry's not doing better than Chris, right? Okay, so that's the names of vectors. Moving on briefly to the next major data structure, and then we'll finish here. That's data frames. So data frames, they're two-dimensional. So unlike those one-dimensional vectors that I'm showing in the little schematic here that were one-dimensional and all had to be of the same type. You see, the elements are the same color. Data frames, they're tabular. They have rows and they have columns, and the columns can have different data types in them. So one column could be numbers, one column could be characters, another could be logicals, for example. So data frames, they're the de facto data structure for most tabular data in R. They're what we use for doing most statistical analysis, and also what we use whenever we go and do plotting with packages like ggplot2, for example. We'll have more on this afterwards. Now, they're arguably the most important data structure in R because they're usually the inputs to those important functions that we'll use. And data frames, just like vectors have names, they can have row names and call names. So we can name the rows and we can name the columns for easy access. For example, if we had gene IDs in a particular down one column and sample IDs or whatever, useful things that will be important when we want to analyze our data later. We can store them in the data frame. So data frames can be created manually, and we rarely do this, but I'm showing it for completion with the function data frame. So here I'm asking the function data frame to create a little data frame with 3 columns. The first one's going to be called ID, and it's going to have the first 5 letters of the alphabet taken from this inbuilt vector of alphabetical characters that comes ready in R. You can have all the letters of the alphabet if you just type letters, and I'm accessing the first 5 letters. So it's going to be A to E in this case. Then I'm going to have a second column called X, and it's going to have the numbers 1 to 5. And a third column here, Y, which is going to have the numbers 11 to 15. And then I print it out. So here's the little printout. In RStudio, I could also click on this thing, the object up in the environment panel, if you see where that is. Or in the console, I can type view to call the view function. This is where the capital V here note. And the input would be that. That would be the input to the function view. And that will bring up a little table view, much like you would see in Excel, for example, to explore or visualize the table of numbers of your data. So now most often we don't create data frames like that. We actually get them when we read data in from some external file. Whenever we use functions like read CSV for comma separated value files, or read delim for tab separated files, or read table for space separated files, or read Excel, or these XLS style formats, or whatever the data format you're reading in, we'll often get data frames from them. We're going to get lots of practice of doing this and creating data frames in this way in future weeks of this class. Actually, next week in particular, we're going to get lots of examples of reading different formatted data in, making these data frames that we can then bring forward to analyze within R. For now, what I'm going to do is list some useful functions for dealing with data frames, and we'll return to these later and learn them more fully when we need them. These include head and tail. This will show the top 6 rows or the last 6 rows respectively. This is useful with the kinds of data that we often deal with in mathematics, because we'll have hundreds of thousands of things in these tables, things that wouldn't open in Excel, but we can read them into R happily. But you can't just print them all out, review them all, but we'll look at small slices of them, like the top or the end, just to make sure they follow our mental model of our data. We can look at the dimensions that will return the number of rows and the number of columns. You can also view those things individually, like the number of rows or the number of calls with n row or n call. We can query or set those names arguments, the row names or the call names, to give or set those names appropriately. We can also use this str or structure function to tell us something about the type of data that's in each column, for example. And there's also the view function that we already mentioned. And then finally, there's this dplyr package, which isn't listed here in the slide, but which is really awesome for subsetting data frames, getting quickly to the subset of data within a big data set that you might want to analyze or look at further, like the subset of upregulated genes in the huge analysis that you've done, for example. Okay, I'll note here finally that vectors and data frames are just 2 of the 5 or so major data structures in R. They are, however, the most important. If I had to pick one more, and this is another one that we'll use quite extensively in this class, it's list objects. These first 3 here, vectors, data frames, and lists, are definitely the most important data structures. Lists, just for now, what they do is they, like the little graphic here shows, they allow us to combine vectors and data frames and other data structures all together into one kind of container called a list to keep us organized, and that's really good for our sanity when we can have results all together. And we often get lists, for example, from functions that we use for modeling, and most bioinformatics functions that we'll use return an answer as a list. So we're going to get experience again at how we access the individual components of a list in our coming weeks. And we'll cover these also a little bit in our hands-on section this week, both accessing data from vectors, from data frames, and also, but to a lesser extent, lists. So our hands-on session this week, it covers those topics, as well as more on calling functions in R, getting help in R, on vectors and vectorization, how this works and how this can be a great advantage to us, on workspaces and working directories. That's how we set up our work within RStudio, as well as RStudio projects, things that really keep us organized and will save our sanity later when we come to have multiple projects on the go at the same time. There are lots of great online resources to help you learn these things. I'm listing several of them here. The major one I want to draw your attention to, of course, is DataCamp. We again see the class website on our Piazza forum for details of accessing DataCamp for free. We have access to the entire catalog of those courses. I'm assigning you some homework through DataCamp this week, and for some of the following weeks we'll have additional homework through there. It's a really useful resource that I encourage you to take advantage of. With that, I'm just going to finish here and summarize our key points for this video. R's basic data types include logical, that's the true falses, the characters, that's the strings, numbers, of course, that's numeric and complex objects, which we deal with less in this course. R's basic data structures, and major ones include vectors and data frames, but also lists and things called matrices. We should understand the basis of using functions. That's, we type the name of the function we want to use. Then within the parenthesis, we give the input to the function that can have multiple input arguments, for example, that are comma separated. We should know how to find what those arguments are by looking up the help functions, right? As well as being aware that this cool feature of vectorization that allows us to operate on every element of a vector all in one go. So unlike other programming languages where we might have to write a for loop to iterate through each element of an array, for example, R will do this all for you, and that's a good thing that saves us time, of course. And finally, that using that help function with the question mark, the name of the thing we want to look up, as well as guided and directed practice through DataCamp, and of course good old Google, looking things up when you need to, they're going to be your friends. So while we're going through these learning and growing pains in R, it's totally natural and expected, and you should embrace this feeling of you learning, right? This frustration, this growth mindset that we want to foster here. As we delve deeper into data analysis with R, and bioinformatics specifically, these feelings are going to, they're not going to go away, but they're going to get less over time. And I'm going to ask for your patience and your understanding as we kind of face these together and guide you through these things all together here. So thanks for watching, and I'll see you next time.